Alright, what's up guys? Let's do another random problem. Let's do a graph problem today. A random graph problem. Medium, nice. Okay. Haven't done this before. Wow, only 581 people have done this. I don't know. Let's not do this one because I want to do ones that are like relatively popular. Nope. Same problem. Okay. Alright, this is 70% though. I want a harder problem. I'm gonna be picky today. I've done this before. Okay. We have something here. 56. Okay. All right, let's work with this. 15 minutes on the clock. Let's go. You have information about n different recipes. You are given a string array recipes and a 2D string array ingredients. The ith recipe has the name recipes I, and you can create it if you have all the needed ingredients for ingredients I. A recipe can also be an ingredient for other recipes. Okay, so we have some kind of dependencies here. For example, ingredients I may contain a string that is in recipes. Sure. You are also given a string array supplies containing all the ingredients that you initially have, and you have an infinite supply of them. Return a list of all the recipes that you can create. You may return the answer in any order. Note that two recipes may contain each other in their ingredients. Okay, so this is a cyclic dependency. So return a list of all the recipes that we can create. So, I mean, it just seems like a topological sort problem. That will naturally just give us a list of all the recipes that we can create. And I'm pretty sure, like, with the topological ordering, if there are any cycles, it won't be added to our list. So yeah, I'm pretty sure we can just create some kind of topological sort. The only thing is, like, we have these supplies. We have yeah, I guess I don't want to worry about that now, but we have supplies we got to worry about. We have recipe names and we have the ingredient lists. So let's look at an example though. So recipes are just like the name of the ith recipe, I guess. Okay. So, okay, recipes 0, we have bread. Ingredients 0, we have this list, yeast, flour. And our supplies consist of yeast, flour, and corn. So, okay. So yeah, we can use these two supplies to create our bread. So, yeah, we can create bread. So we'll put it in our list. Sure. Let's look at this. Bread and sandwich. So yeast, flour, same as before. Now we need bread and meat. Okay. So our supplies are this. So we can use yeast and flour to make bread. And then now that we can make bread, we can use this ingredient, the supply meat, and we're able to make bread now, so we can use bread and meat here to make sandwich. So bread and sandwich should both be in here. And now I'm assuming this will probably give us a cyclic dependency. Burger. What does burger need? Sandwich, meat, and bread. Well, it appears it's not a cyclic dependency, but I can already imagine what a cyclic dependency would look like. Yeah. So, like, for example, let's say our supplies are like A, B, and then our ingredients list is like, well, first let's do our recipes. Recipes is like C and D, and then our ingredients are like A and D, and this would be like B and C. So this is the ingredient list for recipe D, but it requires a C. So we got to look at our C recipe. Our C recipe consists of A and D, but we require a D here, which would, obviously be over here. So you can see there's obviously a cyclic dependency, and I think if we construct our graph correctly, the topological ordering will ignore this. So, okay, let's create our graph. So this will store my graph. So how can I add nodes? Well, I think the first thing is let's see here. So I know that all my supplies are nodes in my graph. I'm just thinking, like, should I add them to my adjacency dict here? Yeah, why not? So for S and supplies, we'll do since we have an infinite number of supplies and we can get them like whenever we want, we have no dependencies here, so there's no edge, there's no directed edge. So yeah, this we can just stick each supply in our graph with no dependencies here. There's no directed edge. Now, okay, how can we go through recipes and ingredients? So we can do for RI recipe ingredient in zip of recipes and ingredients. We know the adjacency for recipe is going to be, well, let's do for, should I just append the list here? I don't know, this feels unnatural because usually I append neighbors. But I think in this case I can just like do something like this. I don't know if I like this because I know that this is going to be a reference to this list, and then if I have this, well, no, these lists are going to be unique references. I think this is fine. So what this looks like in our graph. Let's take like this example, the bread sandwich example. So we're gonna have a node here. Well, we'll have the supplies. So we'll have yeast, flour, and meat. And then we're gonna have bread. And sorry, wait. You know what? In order to do this, we also need in degrees, right? For topological sort. So the supply should have no in degrees. So I'm actually thinking this might be backwards. I think this is like a backwards relationship here. I think we have to go through each ingredient and then add an edge from that ingredient to the recipe, because in our graph, essentially each ingredient required for recipe is going to take part in like unlocking the recipe. So we'll have an edge from each ingredient each element of the ingredient list. Sorry, this is named poorly because ingredient is actually plural. This is a list. But I think let me write this out. It'll be a lot clearer. So for recipe, I'm gonna call this like ingredient list. For recipe ingredient list, we're gonna do for ingredient and ingredient list, we're going to do adjacency of ingredient dot append recipe, and then in degrees recipe equals 1. Right, because these ingredients are pointing to our recipe, so the recipe is going to be accumulating the in degree. Okay, so back to this example. Let me just draw out the graph again. So we have our supplies: yeast, flour, and meat. And now let's look at a recipe here. So our recipe bread, we need yeast and flour. So yeast will I don't even know how I'm going to demonstrate this, but whatever. Yeast is going to go to bread, and then flour is also going to bread. And these are directed edges, pretend. And then what do we have here? For sandwich, we're going to have sandwich here, and then we'll have a directed edge here pointing to sandwich, because for sandwich we need bread and meat. So bread will point to sandwich, and we'll have meat over here. Yeah, you get the idea, hopefully. So meat will point to sandwich. And so when we process our graph in topological order, meat's going to have 0 in degree, flour's going to have 0 in degree, and yeast's going to have 0 in degree. So we'll process these first. So these will come out, and all these edges will go away. And then we'll be left with bread and sandwich. Bread will have in degree 0, we'll take off bread, and then delete this edge, and sandwich is in degree 0. So yeah, that will result in all of these recipes being processed. So I think this works. So now what we want to do here is yeah, so we have our graph, so we need to create our queue for the topological sort. Oops. So queue is a deck, and this is going to be the node for node in adjacency if in degrees node if node not in degrees. Yeah, so this will start with all the nodes in degree 0, and this will be our result. And then while the queue occur, queue left as occur. For neighbor in the adjacency of cur, we're going to do in degrees neighbor minus equals 1 if in degrees neighbor is 0, then we'll put the neighbor onto our list. Think that's it. Yeast, flour, corn, bread. Oh. Wait, what's the actual output? Oh, we only care about right, we only care about the actual recipes. We don't care about the supplies. Okay. So I'm gonna do a little hacky thing now. So we'll create a supplies set, and then if cur not in supplies set, then we'll append to our list. What's unhashable? Oh. Okay. Let's use this test case. What am I doing wrong here? Recipe is bread. Ingredients are yeast and flour. We only have yeast. Oh, okay. Interesting. How do I handle this? Where should I handle this? Oh, okay. Actually, I have an idea here. So this should be like node for node in supplies. If node is not in degrees. I don't think we need this. Okay. So the only optimization here, or like the only issue I don't really like is creating this set here. I think we could possibly clean this up. How can we clean this up? I don't know, but it won't change the overall time complexity, or space complexity. Since, well, no, it won't, because I'm iterating through supplies here. So since I'm already iterating through supplies, one more iteration through supplies isn't going to hurt me. And space complexity, I'm already storing like the graph, which is well, what if we had a lot of supplies that weren't used at all? Is there anywhere else where we're storing supplies? Because, you know, theoretically, like, yeah, this could be hurting us actually. Since we're storing all the supplies. Yeah. I think like theoretically this could actually hurt if we had like a ton of supplies and almost all of them weren't used, because there's nowhere else that we're storing like all the unused supplies. Like here in this graph, we're only storing supplies that correspond to a recipe. Yeah. So I think one way we could fix this would be like store a flag, maybe here. We could do like, this is kind of hacky, but like we could do like a flag here, like node true indicating that it's a supply and it should not be processed, or it should not be appended to our result here. So instead of the supplies set, we can delete that and we can do cur and supply, and then if supply, if not supply, then we'll do this. And then whenever we want to add to our queue, we're going to add the neighbor and false, because at this point it won't be supply anymore. they were only supplies when we initially filled our queue. So yeah, well, didn't really help in the graph, but I think theoretically it does help. Let's see the constraint on supplies. Oh well, supplies length is only 100, but if you think about it, yeah, I think that this would help the overall space complexity. Let's check the editorial. Breadth first search. I don't know, is this slow? N squared seems slow. Depth first search. Seems like this would also be slow. No? Wait, no. I don't know. Topological sort. What's our time complexity here? Same as depth first search? Yeah. It looks like it's the same. Yeah, actually, yeah, you can do depth first search because you can essentially do like a depth first search with post order processing. Because that's essentially like a topological sort type thing. Let me see. When do they append to their result? Why is this so hard to read? Turn recipe for, ow. Sorry, I just hurt my foot. Anyways. Okay. If check recipe set. I don't know. You think they're doing too much here? I think they're doing too much, even though it's less code than what I wrote. Whatever, man. Wait, it's actually more code. Nah, they're doing too much. Well, it's probably less code because they have all this fancy formatting. Anyways, I'm dragging here. All right, I think we got it. Maybe we went over time a little bit, but close enough. Thank you for watching.